Truth table is basically a table that shows the relation between the input and the output in a digital logic circuit. So in this session, we will look into more details on how to actually build a truth table for any logic circuit. Just for a recap, the truth table here shows a logic circuit with two inputs, which is A and B, and one output Z. So normally in truth table, the input will be on the left side and the output will be on the right side. From the previous session, we had take a look at AND gate and its truth table. So the truth table tells us that the output will be high only all of the inputs are high. So in this case, A is high, B is high, then the output, which is A and B, will become high. So this is a very simple example, a very small circuit of only two input and one output. So please bear in mind that it does not matter what size of your logic circuit that you are going to design in the future. You will basically start with this definition of the truth table. So for example, we can actually use this logic gate to represent a security system which has two inputs. The first one, we can use the first input as a, for example, temperature sensor, and the second input is our motion sensor. So the output will be an alarm. So in this case, the alarm will sound, which is become high if the temperature sensor and the motion sensor give a high input. So this is a simple example of how we can actually apply the logic circuits and using the truth table to define our operation diagram. So in this example, I just want to give a simple example of how to build a truth table for a 3-input circuit, which is A, B, C, and then it has one output Z. So the first step is actually to start to build a table and give the 3 input names, which is A, B, C at each column on the left. And then on the last column on the right, we write down the output name, which is in this example is Z. So the next step is to define the combination of the inputs logic. So in this case, we want to know how many rows or how many inputs combination. So based on earlier chapter, we have actually learned of how to determine the number of combination based on the input numbers. So the number of inputs combination or the number of rows is basically 2 to the power of n, where n is equal to actually number of inputs. So in this example, we have 3 inputs. So the combination will be 2 to the power of 3, which is we have 8 combination. All right. And then the output will actually depends on our logic circuits or logic expression. So now let's insert the each inputs on each of the row. So we'll start with the combination of the lowest count. So the count is basically we'll start from 0, 1, 2 until 7. So in binary, it will be 0 is 0, 0, 0, and next we have 1, 2, 3, 4, 5, 6, and 7. Alright, let's look into the example. So here's a logic circuits of a number of gates. So we have one NOT gate here, 2 OR gates, and 1 AND gate. So how will the truth table will be drawn to find out the logic expression for this circuit? Alright, so if you look into this one, so we realize that the first is we have 1 A inputs, B inputs, and Z output. So we have 2 input, and we have 1 output here. Okay, I just put outputs here. All right. So we know from the previous slides, we have 2 inputs, which is A and B, and we have 1 output. All right. The first step is actually to fill in the first 2 columns, input columns A and B, and count the combination from counting up in binary. Okay, why do we have a 4 combination? Because if you still remember, we have 2 inputs, 2 to the power of 2, then we have a 4 combination, which is actually count from 0, 1, 2, and 3. So each of this number here is represented by the binary number of each of these decimal number, 0, 1, 2, and 3. The next step is to find the outputs from each gates respectively. Well, the easiest way is to start from here, from the input side, which is A and B. So normally the input will be on your left. So we have input A go through a inverter or a NOT gate, and we have the output is A bar, which is the inverse of A. And from here we have all gates with input A and B, so we have output A or B, and then both of these A bar and A or B will be the input to this AND gate, and this is the output from here. And finally, both from A or B and the input from here will goes into the last OR gate. And finally we have the output Z equal to A or B, or A or B and A bar. Alright, so this is the final output for this logic circuit. And in the final step, so we have to fill in the output value. So fill in the output value based on the input combination of the logic equation. So what means by this is actually, so this is our Z or Z. So A or B, so 0, 0, so this part will become 0. And this is also A or B, become 0. A is 0 and A bar is equal to 1. And 1 and 0 is become 0. So 0 or 0 is actually equal to 0. So that's why our output here is 0, because our input is both 0. So you have to repeat the process until the end, and supposedly we have this output value based on this input combination.